Collision theory explains why chemical reactions occur in a way that we can predict how parameters like temperature, concentration, will affect the rate of a chemical reaction or the reaction kinetics. So according to collision theory, a chemical reaction will occur when three things. The reactants collide. So in this example, where A is reacting with BC to form A, B, and C, the atom A must come in contact with the molecule BC in order for a reaction to occur. The second thing is they have to collide in the correct orientation. If we have A colliding or coming into contact with BC where it's colliding with B, then we can have a reaction occur. But if in contrast A is coming in and it hits C before it comes in contact with B, it can't form its new chemical bond with B, and so a reaction might not occur here. So they have to be in the right orientation when they collide. And then the third item is when they collide, they have to have enough energy for the reaction to take place. And as we go through a chemical reaction, from reactants to products, we go through a higher energy transition state where the reaction has started to occur. There might be an energetic cost for starting to weaken the bond between B and C so we can form a new bond with A and B. This energetic cost is called an activation energy, or E sub A. And that's an input that must occur. If the reactants collide and don't have enough energy to get over that hill in some ways, then they can't form products. So those are the three criteria: that the reactants collide, that they collide in the correct orientation, and that they collide with sufficient energy. We can use these three rules to start talking about how different parameters might affect the rate of a reaction. So the first one I want to talk about is concentration. The concentration of reactants will affect the rate of reaction. Higher concentration of reactants will increase the rate of the reaction. And we can look back to these three rules to understand why. If there are more reactants in the same space, we will see more frequent collisions, okay, and therefore a higher rate of reactions. The second main effect, or parameter that affects it, is going to be temperature. As we increase the temperature is proportional to the average kinetic energy of these molecules, and so at higher temperature, the molecules are moving around more quickly in solution. At higher temperatures, we would expect more frequent collisions. But higher temperatures will also increase the proportion of molecules that have sufficient energy to get over this hill. A temperature here, we might have only a few molecules that have enough energy. Might look a distribution something like that, and as we increase the temperature, we might have many more molecules with enough energy to get over that hill. The third factor I want to mention is surface area, and this applies only to heterogeneous reactions. So say you're burning firewood. The interaction surface where the oxygen gas is in contact with the wood is where the reaction is occurring. And if we increase the surface area, if we chop up the wood into kindling, there's more surface where that reaction can take place. Greater surface area means more frequent collisions, which allows the reaction rate to increase. And the final example I want to mention is something called a catalyst. A catalyst is a chemical that's added to a reaction but is not produced or consumed in the overall reaction. Instead, what it does is it offers an alternate reaction pathway, a reaction pathway that has a lower activation energy than the original pathway. And by dropping this activation energy required to get a reaction to go, it will increase, often greatly increase, the proportion of molecules that have sufficient energy to undergo a reaction, or proportion of collisions that will have sufficient energy to undergo a reaction. So reaction rates will increase as we increase concentration. They'll increase as we increase temperature. They'll increase as we increase surface area, and they can be increased by adding a catalyst. Conversely, as we lower temperature, say we put a jar of milk in the refrigerator, we're lowering the temperature, we're going to lower the rate of a whole bunch of both biological and chemical reactions that are taking place, and lengthen the time the milk's good before it spoils. As we lower the concentration, say as a reaction proceeds and some of the reactant is consumed, if this is the concentration of a reactant, as the reaction proceeds, it's consumed to produce products, that concentration will go down. And for many reactions, as that concentration of the reactant goes down, we see the rate of the reaction drop.